Ogutu, how are you? That's the challenge of multitasking. Anyhow, life has to continue. I was saying that the method of sampling can be broadly categorized into two. We have what we call the random, and we have the non-random. And for the random, we have simple random, we have stratified, systematic, and multi-stage. And for the non-random, we have judgment, quarter, and the cluster. So when we talk of the simple random sampling, this is where every item of the population is given an equal chance of being included in the sample. Since the selection of the items in the sample depends entirely on chance, we normally say that each member of the sample has an equal chance to be selected. Now they are classified into two. We can further classify the random sampling into two. We have what we call sampling with replacement. And sampling with replacement is when we have a finite population and the unit that is drawn and observed is replaced or is taken back to the population, which means it has a chance of again being picked again. And then we have the sampling without replacement. And without replacement is to mean whenever we take all that unit, or whenever we draw the unit now from the entire population, we observe it and put it aside. So random samples may be selected either with the help of, or this is a good example is lottery. When you are doing lottery, the cards are shuffled or the raffles are shuffled, and then we picked one from the raffles. That's what we mean by random sampling. Then you have the stratified, and stratified is the case where the population is now divided into homogeneous groups, all groups with the same characteristics, and this is what we normally call strata. So when we identify, for example, you are admitted in a certain year in a certain semester. So we can easily say that you are in year 4, semester 1, year 4, semester 2. There is someone who is in year 1, semester 1, because the unique characteristic of stratifying you was the date of entry or the year of entry. Then for the systematic sampling, this sampling where it's simple random sampling where we now arrange our data in ascending order, right? Let's say we have units starting from 1 to 1,000. We are going to arrange them, or let's say, yeah, we have 1 to 1,000. Let's say we want to pick the 20th and the 50th. So in the ascending order, we'll just count. Once we get now to the, I have to keep on admitting those people who are joining in. Admit all. Abraham Y. Dennis. I don't know. These are mistakes that was unanticipated. So I was saying that in the systematic, we arrange this data in ascending order or descending order, whatever the order, and then we pick. For example, you can be asked, pick the 30th or the 40th. In your order, systematically, you can be able to count the 20th or the 30th item and pick. And then for the multi-stage, it is more of or less like the stratified. It is similar to stratified, only that we now divide. We divide our sample into what we call the geographical or the location. For example, you can talk of a country that is divided into counties. Kenya has 47 counties. So when we talk of the multi-stage, we'll be talking of now the particular county from the multi-stage sampling. And when we come now to the cluster, or when we are talking of the multi-stage, the multi-stage I've said is similar to the stratified, but we are now putting them into the geographical location. And in cluster sampling, it is more or less the same, because what happens is we take now the geographical regions, and then from the geographical regions, we can now talk of the single households. For example, if you are to do sampling for the people who use matatus, it will be unfair to go ahead and admit Ndumia. Have to keep on admitting these people who are joining. So you have to go to the particular group of people or cluster that are affected by the characteristics or the traits that you are looking for. Then from the random, we have the non-random, and in random we have the first one is the judgmental sampling, and this is where now the interviewer selects who to interview, believing that this is the right or the particular unit that is to be selected has the fundamental traits that they are looking for. When we talk of the quarter is when we now classify our data into quarters or into more or less like strata, but this one is non-random. So when I talk of the quarter, for example, you can talk of job groups. Yes, we have teachers or we have the lecturers, but these lecturers will be subdivided into some unique job groups. There are those that, let's say, teach the science courses. There are those that teach the humanities, or there are those, let's say, we have the senior, we have the tutorial fellow, we have the, so you can see the quarter will be the characters that are drawn to quantify that particular group. That is the quarter sampling. So I thought it is good to go back to what we had learned before we come into our today's topic. So we are talking of the central limit theorem, and when we are talking of the central limit theorem, the theorem was introduced by a scientist by the name de Morville. And according to him, if we select a large number of samples using simple random sampling technique from the population and determine their means, or we put now the different sample, we have a sample of 15, 15, 15, and we get their means. The means of these individual samples will not be equal. So we are going to have the mean 1, the mean 2, the mean 3. So the distribution of these sample means will tend to be described by the normal probability distribution with a mean mu. So when you are talking of the mean mu, that symbol, the symbol that we are using here, allow me to admit. Yeah, when we are talking of this mean, this is the mean of the population. Of course, then we are talking of the variance, and variance is supposed to be standard deviation squared. But you can see we are dividing by the particular means that we have. So it is true, even if the population itself is not a normal distribution, or the sampling distribution of the sample approaches the normal distribution, the particular or where the sample is taken can be approximated as a normal distribution. And more or less, we'll be having this increasing now depending on the sample size. Now we have different types of distribution. We have the population distribution and we have the sample distribution. I want us to compare the two. So when we are talking of the population distribution, we are talking of the individual values of the entire population. So we are talking about the entire population. If the population has 1,000, we are talking of the entire 1,000. So if we get the mean of the entire population, we'll be talking of the mu. But when we talk of the sample distribution, we'll be talking of the individual values of the single sample. So suppose we split our population of 1,000 into quarters of 100, 100. We are going to have 10 samples. These samples, when we get their means, we are going to have mean 1, mean 2, mean 3, up to mean 10. So when we talk of the sample mean, which is denoted by X bar, it is not usually the same as the mean of the entire population. They'll differ. So even when we come now to the distribution of the sample means, now a sample of size n will have been taken from the parent population of n, which is capital. So we are talking of the population, which is denoted by capital N, and we are talking of the sample, which is denoted by small n. And this is, when we talk of this, we are talking of the, let me illustrate here. So we are talking of the mean of the sample. The arithmetic means of the sample is denoted by X bar. This is supposed to be X bar. This one here, X bar. And this is mu. This symbol is called mu. So when we are talking of the arithmetic mean of the entire population, we denote it by that Latin symbol. Then we have the standard deviation. For the sample, we denote it with a small s. And for the entire population, we use this symbol here. We call it sigma. And then for the number of items, I've said for the sample, it will be n, whereas we are going to denote that of the population with capital N. So that is that. So if we split our n, which is the entire population, and we get the different means, whatever we'll be getting will be sample means. So we are going to get x1 up to x10. And this is normally distributed, or nearly so, according to the De Morville's theorem. Now, it can be described by its mean and standard deviation. So we'll be seeing. And when we are talking of the standard deviation here, we are talking of the errors. These small or these sample means, each one will be deviating from the mean of the entire population. Now that deviation is what we call now the standard error. I know in statistics 1, you talked of the variance, or when we are measuring how far the set of number are spread out, we normally talk of the variance. And I've said that variance is now the standard deviation squared. So the variance of 0 indicates that there are no identical values in the sample means. But momentarily, because we expect that each of the sample mean will be behaving allow me to I hope they have joined. Very well. So I'm saying that this particular sample means each sample mean will, of course, have its normal distribution. Now, this normal distribution, we'll be comparing it with the mean or the variance or the standard deviation of the entire population for us to draw what we call, or for us to have a statistical inference, or to make, or to infer, to make a comment that we can quantify using data. We will be inferring our sample mean with that of the entire population. Robert Obado, welcome. So this standard deviation is what we are calling now the standard error. And the standard error is given by this formula. So we are talking of the standard deviation of the sample population over the square root of the number of items. And this formula is satisfactory normally for the larger samples. And when we are talking of the larger sample, because we are the statistician, we are defining our sample as any number that is more than 30 will be taken as a larger sample, or the 5% of the entire population. So we are talking of our n being greater or more than 30 in number, or 5% of the entire population. So if we are talking of 1,000, our 5% would have been 50. If we were talking of 100, our 5% will be 5. So what is happening here, you can see, we are replacing our standard deviation or the deviation with the error for purposes of distinguishing the two. So whereas for the population, we talk of the standard deviation, we'll continuously use standard error when we are talking of the sample size. So the smaller the standard error, the greater the precision. And I've said when it is 0, it shows that we have identical values, but we expect that the number that we'll be getting from the sample, if the data is normally distributed, it will be spanning from -1 to 1. Yeah, so it will be a number between -1 to 1. But when we come now to the variance, we don't recognize the negative numbers. A number can only deviate positively. So we cannot talk of the negative deviation. Now let's look at the statistical inference. And this is normally the process of now drawing the conclusion. To a statistician, data is just data. It is meaningless. It is after the analysis that you give meaning to this data. So if you've not analyzed, you cannot really say that this is how the data is behaving. And some inferences can lead you to a wrong conclusion if not well defined. So the process of drawing conclusion about the attribute of the given population is based upon the information that is contained in the sample or whatever the statistician was looking for. So I've said our data or the symbols is as highlighted. Let's start with the statistical estimation. So whenever we'll be talking of the sample, we'll be using, this is X bar, this is not X. So the arithmetic mean, we denote it by X bar. For the population, it is mu, this symbol is called mu. Maybe I can expand this for, there we are. So this is mu, this is X bar, standard deviation, small s. For the entire population, we talk of sigma. And then for the number of items in the sample, we talk of n for the sample size, whereas for the entire population, we talk of n. So I want us to start with, take this back. So I want us to talk about the statistical estimation. And because I've seen, again, let me admit Ndumia and I can see we have quite a so I was talking about the statistical estimation, and this is the procedure of using now statistics to estimate a population parameter, where we either divide our population into, or we do what we call the point estimation, where the population parameter is given by a single number, or we can do what we call interval estimation, where an estimate of population is given by a range. So you normally get a range, and I've given an example there. For example, a bus is meant to take a class of 100 students. So our population is 100. That is our N for a trip. And it has a limit to carry a minimum weight of 600 kgs. Don't know how heavy these students are. Yeah, it's like they are 6 kgs. Ignore that. So we are talking of the maximum weight of 600 kgs. That is what the bus can handle, of which it can carry. And the teacher realizes that he has to find out the weight of the class, but without enough time, he had to do sampling. So he picked 25 students randomly. So we have our N is 25. This is the sample size. So these students were weighed, and the average weight recorded as 64 kg, right? So this will be our now the sample mean, it is 64 kg, with a standard deviation or a standard error. The small s is a standard error. So now using this, the teacher intends to estimate the average weight of the whole class. So the average weight of the whole class will be our mean for the population, which is denoted by mu. So by using statistical parameters, our standard deviation and the sample size will be able to give us this. And we normally give the characteristic of how or what a good estimator is supposed to bear. To start with, it's supposed to be unbiased. And by unbiasedness, we mean the value of the statistics should be equal to the population parameter, right? Then it should be consistent with the data. So where an estimator is values more closely approaching to the population parameter, we call it a consistent estimator. Then we have efficiency. Where the estimator has small variance on repeated sampling, we call it efficient. So we are talking of if we were to take the, let's say, another sample of 25, we expect again, if we were to take another sample of 25, we estimate or we are supposed to get more or less 64 kg. Let's say 63.9 or 64.1. That way we'll have said that our sample is sufficient. Then we have sufficiency. Sufficiency means enough. So where an estimator uses all information available in the data concerning the population, we say that it is sufficient. So this will help now the statistician infer or draw a conclusion on the sample to represent the entire population. So research are very expensive. And you've seen even the government, the census is not just taken after 10 years. They do so because it's a very expensive exercise. But occasionally, the Kenya National Bureau of Statistics, now depending on what they want from the population, maybe they want to know the manufacturing industry. They will pick, so they can say the population of Kenya right now is a staggering 50 million. If we are having, let's say, 100 industries that are processing fast-moving goods, they can say out of the 100, we can take a sample of 30. Then from the sample of 30, they help now infer for the entire population. Because doing the exercise for the entire population will be really expensive and hectic for the Kenya National Bureau of Statistics. Again, there are chances that if they choose wrongly, out of the 30 in the 100 manufacturers of fast-moving goods, they are going to get wrong conclusion. So when we are talking of the good estimator, the statistician should make sure that whatever they have chosen to represent the entire population. I had given an example. Let's say you want to do a research about those people who use public means of transport. It will be very unfortunate for you to start giving your questionnaires to those people who are driving private cars. They'll give you a wrong conclusion. It will be very unfortunate if you go and try to dish out your questionnaire to the people who are, let's say, somewhere in Samburu. They are pastoralists. So it takes time before these people even use a vehicle. They normally, or people are saying that they cannot see. Is it now audible? Are you able to see? That was Jenga. Jenamo, are you able to see? Abraham Nyaga, I said I've given people time to go and upload late assignments until 4. So even if you are locked out by either school fees issue or you are at work, kindly do so. You have until 4. So I was giving an example of you are doing a research on people who use public means of transport. Going to the private car users will not give you good inference. If you go to the people who normally walk, and these people are not using vehicles, daily or otherwise, again, you are going to lose it. So in other words, we are saying the statistician has now the power of making sure that whatever the estimator that they use will be used to represent the entire population. Then we go to the confidence interval. We normally rate our confidence, our degrees of confidence as either 95% or 99%. So if you are using a sample mean and you want to estimate all your confidence limit, now when we are talking of the limit, we are talking about the range. Or how do you quantify your data? How far do you want your data to vary? What's the probability of getting the right data? So we normally use 95% or 99%. And this one, you can use the mathematical tables. If you look at the 95% level of confidence, it normally gives us 1.9 if you are to put it on a Cartesian plane. And then for the 99% degree of confidence, we normally oscillate between negative 2.5 to positive 2.5. So we'll be using that later on in our examples. Now, for the large samples, we said that our sample size should be, or we are dealing with an n that is greater than 30 or 5% of the entire population. Now, when we are estimating the population mean, here we will assume that if we take a large sample from the population, then the mean of the population will be close to the mean of the sample. And we normally follow these 5 steps. To start with, we take now a random sample of the n items from the population. From this, we compute the sample mean, x bar, and its standard deviation, or the standard error, if I may say. And after now getting the standard error, using the formula, we choose a confidence limit. So we can either go with 95 or 99%. And then from there, we estimate the population mean. And this is the process of estimating. We know that our population mean is mu. So we are going to get the mean of the sample. This is the arithmetic mean of the sample. We add the appropriate number. And the appropriate number, this is what we are going to draw as our confidence level. If it is 95%, we'll go with 1.96. If we'll choose the 99% confidence level, we'll go with 2.575. Let's have an illustration and see. We have an illustration there. Go through it. So we've been told that can go through the so there is our example or illustration. So we are saying that the quality department of a wire manufacturing company periodically selects a sample of wire specimen in order to test for breaking strength. Now, past experience has shown that the breaking strength of a certain type of wire are normally distributed with a standard deviation of 200 kgs. A random sample of 64 specimen gave a mean of 6,200 kgs. Find out the population mean at 95% level of confidence. We have our steps. So the first step is to take a random sample. But this one, the sample is already given. So it's like step 1 and step 2 are provided. Yeah, because we've been told that the mean is 6,200 kgs, isn't it? So can we get the standard error? So our standard error will be the standard deviation. We divide by the square root of the sample size. So we've been given our standard deviation is 200 kgs. So it's 200 kgs over square root of 64, which is 8. So 200 divided by 8 is 25.
25.
Yeah, 25. So you can say that our standard error is 25. Yeah. So with that, can we be able to get the population mean? So you said our population mean will be the sample population. We add the degrees of confidence, and then we add, we multiply by the standard error that we have obtained. You've been given this. So what will be our population mean? At 95% confidence level, we work with plus or minus 1.96. You can get this from the Z tables. But in the interest of time, we know that it is plus 1.96. So we are taking the sample size mean, which is 6,200, plus or minus 1.96 into, we've gotten our error as 25. So this is how it will be. So we are talking of 62 plus, I get plus or minus. I don't have a rich text. Then we have 1.96 into bracket 25. So what do we get? For the plus, there are people who are keeping on leaving the meeting and coming back. What do you get?
For the plus is 6249.
6249. 6249. For the minus?
6151.
61?
51.
6151.
51.
So
Yes.
we'll be talking of 6151 to 6249.
62.
So we'll say that at 95% level of confidence, our population mean will be in between 6151 to, is it 2 or
62,
and? No, it should be and. No, these terms, these conjunctions have a meaning in statistics. So we are talking of our, at 95% level of confidence, our population mean will be in between 6,151 and 6,249. So we expect, because our data is a normal distribution to mean it is not positively skewed or negatively skewed. So we expect that our population will be drawn between 6151 and 6249. Are we there?
Yes.
Then we have now a situation where the population is relatively a small size. Now we've assumed that this is a large sample. So where the population is relatively a small size, the sample size will also be smaller. And it could even go below the 5%, which we are calling our limit for the large sample. So if this is the case, we have what we call finite population correction factor, FPCP. And this is normally an adjuster. So we are going to adjust our sample size using this factor. Yeah? And all over square root of now the entire population, we minus the sample size of the with the units of the sample size over n minus 1, where n, of course, is our population size and our n is the sample size. Someone may ask, where are we getting all this? Now, some of these formulas, they are drawn from a lot of validated tests. So scientists, after several observations of the statisticians, they'll come up with an adjuster, which more or less tries to bring now the small size sample into a near normal. So when we are talking of a relatively small size, to make it near the normal distribution, we normally use this factor to multiply. You can remember when you are doing the repeated, when we are doing the repeated or the data that was repeating itself, we used a small adjuster, the t raised to 3 minus t over t minus 1. You remember? So this is one of the sort. And let's see, we have an illustration here where a manager, let me take it to the next page. So we have that a manager wants an estimate of sales of salesmen in his company. That's the data that the manager wants. A random sample of 100 out of 500 salesmen is selected, and the average sales are found to be 75,000. If a sample standard deviation is 15,000, then find out the population mean at 99% level of confidence. So there we are. Where do we start? So we still follow our steps, only that our final answer will be multiplied by the factor, which is now the FPCP. So our first step is getting the mean. We have the mean?
Yes. Come on, 75,000 is the mean.
Yeah, we have our 75. Our X bar is 75. You have to be very categorical. Is the mean of the sample or the population? Of the sample, right? So the sample mean is 75,000. What's our N? Capital N.
N is 500, capital N is 500 because it's the total number of the population.
Yes.
Then small n is the 100, which was chosen out of 500.
Exactly, exactly. So we go on. So you've gotten our, so we can get the standard error. So can you get the standard error? The standard error will be, our standard deviation is 15,000.
Standard deviation, which is 15,000. Yes.
Over the square root of 100.
Yes. Which is 1,500, 1,500.
1,500.
Yes.
Now we multiply by our factor. So can we get our factor?
It's 75,000 plus or negative 2.575 into bracket of that 1,500.
Have we gotten the factor?
Factor. See, try someone. So we are going to the choice confidence after the nini.
No,
After finding the, pardon?
Yeah, come on, exhaust your point. There is something that you are saying.
After getting the nini, the standard error.
Let me take you back to the, yes, we are here. After taking the standard error.
Yeah. We were told to choose a confidence of 99%.
Yes.
So we are going to go there. We take 75,000 plus or negative 2.575 into 1,500. Then we get 75,000. The plus equals to 7,000, 78,000 mean 862.5, and the negative is 70,000 plus 2.5.
So we are talking of
the negative 130.5. 137.5. So at our
and the upper limit is
upper limit 8,000.
Allow me to let me write the figures here. So we are talking of 71.
71 is the lower, 71,137.5. And the upper limit is 78,862.5.
862.5.
That's at the choice of 99%.
Very well. Now let me take you back. If you look at our steps, it is at step number 3 when we are computing the standard error that we are likely, this should be formula, that we are likely to get the error of the entire population. And if you recall, we've given the characteristics of a good estimator. If at the standard error we are able to make all if we take the standard error erroneously, our data will be erroneous through and through. I want us to multiply our estimator or the factor at this point. What is our factor? Our factor will be the square root of 500 minus 100. That is 400 over 499, isn't it?
Yes.
What do we get?
We get 0.80. 0.8.
So our FCP is, we are getting
400 divided by 499 is 0.8.
Is that once
then
you
if
get
you find the square root, it is 0.
When you get the square root, you are getting?
Pardon?
I want the answer after you get the
when
square root.
When you get the square root, then 0.0.
0.0.
Excuse me, Mwalimu.
Yes.
Point.
Okay. Why are we dividing by 499 instead of 99?
We are
supposed to be 99.
Yeah, not 499.
Oh, it's 99. Yeah, our capital N is 500 minus 100. All over small n, which is 100 minus 1. So we are going to divide by 99, right? So what do we get?
It's 2.
We are getting 2.
If you get the total square root, it is 2.
So what is our estimator? What's the value? What's the value of the FPSF? FP.
The value is 2. Square root.
He said that it will only be useful if we get several calculators to be collating these answers. If we get answer from one, those are the dangers of a single-sided story. No, we take it as gospel truth and we move on, and we are getting erroneous. So Jackie has gotten
The square root is 2.01.
2.01. So Jackie, in your previous calculation, you had used 499 or 500, all 99.
It is 99.
You had
It is
used
2.01 exact, but me, I rounded off.
So I want us to see whether we'll get the same answer. So I want us to take, at 99% level of confidence, we are going to work with 2.5. Let us just even truncate, 2.58, yeah? So we are talking of 75. That's our mean, the sample mean. So plus or minus, there's someone who has put 2 gadgets on. Why don't you switch off one gadget? Or you mute. I think we are now better. So 2.58 into bracket 2.01. Want us to see to compare the answer. What do you get? Upper limit for the plus. Evelyn.
75,000.
75,000?
005. 0.18.
0.18. 0.58.
Yeah.
Just say 0.9.
185.
185.
Yeah.
So 0.2. That's okay. When you use negative, what do you get?
$74,994.81.
74.
994.81.
994.41.
81.
81. So 0.8. Jackie, can you see the difference?
Yes.
So it depends. It really affects. If you are going to ignore the factor when you are quantifying the standard error, remember the reason why we are getting the standard error. We want to know how far our sample mean has deviated from the mean of the population. So it is at this point that you are supposed to multiply with our factor, because this is what will give us now the right estimation. If we come and add it when we are looking at the population mean, we'll have already entered into a mess. Are we there? So we are getting the standard error of the mean. It is at that point, because our sample size was relatively smaller, we want to bring it at par at that point before we come to the population mean. I think that is clear to everyone, right? Mary Kenodia is someone. Mary Kenodia. Mute yourself. Like Mary Kenodia has already started her Friday, very in a noisy background. Well, let's look at the estimation of difference between two means. Now we know that standard error of sample is given by the value of standard deviation, sigma. Now this one is of the population. When we talk of sigma, we are talking of the standard deviation of the population divided by the square root of the number of items in the sample. Now, but when given two samples, the standard errors will be given by, now we add, and this is where the student go wrong. So you can see we are trying to get now the difference of the two means. So if you come here, the common wrong answer will be drawn if you use a negative sign, because you are going to get different results. Are we there? So we do estimate the interval, not from the mean, but from the difference between the two sample means. So I think that is clear. So when we are getting now the difference of the sample means, remember we are adding, because these are the small errors that we are going to quantify somewhere on the way. Now the process is still the same, but the appropriate number of confidence level does not change. So the confidence interval will be given by the formula. So you can see what is happening. Just the normal steps that you've used in getting the population mean. But at the end here, we are getting now when we talk of the confidence level, we are still using our confidence level. I want us to look at the illustration. Numbers don't lie. So you have the illustration there. Given two samples, A and B, of 100 and 400, and having a sample mean of 7 and 10, and a standard deviation of 2 and 3 respectively, construct confidence interval at 70%. Who has mathematics tables? I think I have one in my shelves. I can check there. Let me check. Try to digest the question as I check the confidence interval of 70. So we are given two samples here, A and B. I'm looking at 70. At 70, it is 1.04. 1.04. So that will be key when we'll be winding up on the population. So we go. So we've been given two samples, A and B. The sample mean of A is 7, that of B is 10. N1 is 100, N2 is 400. Standard deviation is been given the standard deviation. We've not been given the standard deviation. No, we've been given. It is 2 and 3. So can we get the standard error of the samples of A and B? What will be the standard error? We have the formula here. I've said you just need to know that we are adding. So that's our formula. So our standard deviation squared will be 2 squared is 4. So 4 over 100 plus 3 squared is 9.
9 over 100.
Yeah, 9 over 100. Wonderful. What do we get?
Over
It
TB
is 9 over 400. 400, sorry. 9 over 400.
I've gotten 0.36 as its square root, as the square root of all.
Square root of all.
Yes, 0.36.
0.36.
Mm.
I'm waiting for people to confirm. So at 70%, we've said at 70% confidence level, it is 1.04. What do we get? We are just adding or subtracting at the Z scores. So what are you getting? What is our answer? You say 0.3. What's the standard error, Jackie?
0.36.
0.36.
But can I ask a question?
Kindly do.
This S, where we have the mean of A and the mean of B, where we have been told to subtract, will it affect the whole nini?
Will it affect the
whole calculation of what we are doing?
We
As
are
in
not.
this.
We are not subtracting. You see what will happen? Let's just do it practically. So we'll be having plus or minus. You've said at 70%, this is the corresponding figure on the Z tables. So 1.04. Then our answer was 0. Our answer was, give me the answer.
0.25.
0.25.
25. Yes.
There we go. No, our x1 minus x2, sorry. This is not 0.36. This should be, what is the mean one? It was 7. Is 7 minus
Yes, mean
10.
one was, yes.
Sorry. I think that is what Jackie was asking, isn't it?
Yes, that is what I was asking.
Okay. So what do we get? This -3. Of course, it will affect. On the upper limit, when we add,
Excuse me?
yes.
This 0.25, the standard error that I got was 0.36. So
What?
I'm wondering where the 0.
It is 0.3?
36.
36. Where did I get 0.25?
Jackie, how did you get 0.36?
Some people got 0.25.
Yes, we got
Yes.
0.25.
How did you get 0.25?
Jackie, you're supposed to find the square root of 0.04 plus 0.0225.
What did you get here? What is 4 over 100?
0.04.
0.04.
Then
And
9
then we add 9 over 400,
which is 0.0225. You get 0.0625. Then you find the square root, which is
Jackie. No.
we are losing you.
because it's like
So what are you getting? What's the answer?
25, the square root is 25.
So
Yes, it is
the square root is
0.25.
0.25.
Yes.
Yeah, I must have gotten the 0.25 somewhere. Jackie, have you confirmed?
You may confirm. I used 9 over 100 instead of 400.
Okay. Then give me the answer.
When you add, you get negative 2.74.
Negative 2.74.
And negative 3.26.
2.74.
Yes.
And
Negative 3.26.
negative
3.26.
3.26. What do you think about this answer? Good people.
It's decreasing, coming from negative 0.274 to 1.
It's decreasing. I want an answer like a statistician, a statistics student. Can you deviate negatively? There is a reason why we square our deviation when we are looking at the variance, isn't it? Why do we square? We do that to avoid the negative answer, isn't it? We say that variance is always non-negative. Do you recall? Do you recall? I'm giving you some time to recall. So in this case, we are going to assume the negatives. When we are giving our answers, we give our standard deviation as absolute figure. And by absolute, I mean our X bar is supposed to be an absolute. We are supposed to have the answer. We ignore the negative sign. You cannot deviate negatively. So we'll be talking of two steps, 2.74 and 3.26 steps, but not negatively. And the reason why, when we are doing the variance, the reason why we square our standard deviation is to avoid the negative sign. Tuko pamoja? We have another illustration there. I think that illustration, you will do it on your own. You see in the portal. I want us to look at the estimation of population proportions. Should be the last one. So this type of estimation applies at the time when the information cannot be given as a mean or as a measure, but only a fraction or as a percentage. Yeah. So at this point, or when the estimation can only be quantified as a fraction or as a percentage and not a whole number, the sampling theory stipulates that if repeated large random samples are taken from a population, the sample proportion, P, will be normally distributed with means equal to the population proportion and standard error equal to this. So when we come to the fractions, on when we are talking of the proportions, we are talking of the probability. So numbers between 0 and 1, but in fraction form. They are not whole numbers. So when that is the case, our standard error is given by the square root of PQ, and we know that P is equals to 1 minus Q. Any population, P plus Q is equals to 1. So if we want to illustrate our Q in form of P, it will be Q is equals to 1 minus P. So I'm taking you back to the probability. I hope you have recalled. So we are talking of our P, Q over N all under square root. But we know that our Q presented in form of P is 1 minus P. Tuko pamoja? So the procedure of estimating a proportion is similar to that of estimating a mean, only that we have a different formula for calculating the standard, only that we are now changing them with into P and Q over N. Can you try this? You've been told that in a sample of 800 candidates, 560 were male. Estimate the population proportion at 95% degrees of confidence. So you're looking for the sample proportion P. So what is our P? Our P is 560 over 800, isn't it? What do you get as the proportion of male candidates? 560 over 800, what do you get?
0.7.
0.7. So we can say our P is equals to 0.7. So what is our Q? You said Q is equal to 1 minus P. So what will be 1 minus P?
0.3.
0.3. Just that. So we have everything. So we apply them in the formula. And the formula is our standard error is P multiplied by Q over N. So 0.7 multiplied by 0.3 all over 800. Then you get the square root. What do you get? What is our SP? I'll copy this.
Zero 0.016.
0.016.
Yes.
Am I getting so small number? Because I've copied. So we are getting 0. Can bring this here and make it larger for everyone to see. So my figure here is, well, we've been given 0.016. So that is our standard error. So can we get the population proportion? At 95% level of confidence. So our population proportion, we are looking at the males, isn't it? So we've already gotten our P, or the probability of male is 0.7. So plus or minus into the bracket, no, 1.96 to the bracket 0.6. So what do we get for the upper limit? This is plus. What do you get?
For the upper limit is 0.73.
0.73.
And the lower limit is 0.69.
0.69. and 0.7.
3.
3. So what we know is that the probability is supposed to be between 0 and 1. So if we were to get 1 or a number that is outside 1, 0 or 1, then we are wrong. So in other words, we are saying that our probability or our estimate for the population, the boys or the male candidates will always oscillate between 0.69 and 0.73. Tuko pamoja? So you can try this at home. I want to bring the last one. The estimation of difference now between the proportions. We'll be doing the small samples in our next class. So forget about the small samples. So the estimation of difference between population proportions. Again, we go back to the probability. So let the two proportions be given by P1 and P2, respectively. So we are getting the difference. It's just like the latter case where you are getting the difference of the means, this case. So see what you are doing, you are just getting the, and I've said the logic here is to make sure that in between here, you make sure that this is a plus. This is where students go wrong. So the examiner will just be testing on whether you know when you are doing the differences either between the sample means or the sample proportions, you know that when you minus on this end, when you come here, you are going to add. Are we together? So I think that is clear. All the other factors held constant. Our Q is still 1 minus P. Of course, then you use the level of confidence that you've been given. This is our Z. Yeah? So we go on. Do you have a question in that relation? I don't have a question. I'll be looking for a question from my archive, then I attach it in your, I'll put it in the portal. We try it from the portal. Any question? Do you have a question?